Welcome to Basics of Finite Element Analysis Part 2. This is the 5th week of this course and today is the last day of this week. What we will do is we will conclude our discussion on interpolation functions for linear triangles, and in the last class we had started discussing singular and non-singular matrices. So, what we are trying to do in this particular endeavor is that we are trying to express C's in terms of U's. What are U's? Physically, what do U's represent? They represent the values of unknown variable at nodes. So, U1 represents the value of U at node 1, U2 represents the value of U at node 2, and so on and so forth. So, what we are trying to do is these C's, they do not have any physical meaning. So, we are trying to express C's in terms of U's. We do not know U's also, we know x1, y1, but we are trying to express C's in terms of coordinates of the nodes and the displacement or the variables at those specific nodes. So, that is what we are trying to do, and in that endeavor we had said we had developed this expression expression 4 where U equals a 3 by 3 matrix A times a C vector, and we had said that this can be inverted only. So, I can express C in terms of U only if I can invert A, and I can invert A only if the matrix A is non-singular. Okay. Now, what does a singular matrix represent? This is another important thing to understand. What does this matrix represent? Matrix A is nothing but a representation of the coordinates of the nodes, right. X1, y1 is node of coordinate of first node, x2, y2 is coordinate of second node, and so on and so forth. So, matrix A represents coordinates of the nodes of the element. Now, if you have 3 nodes 1, 2, 3. So, this is x1, y1, x2, y2, x3. So, this is x3 and this is x2, y2. Okay. Here x2, y2, the coordinates of this are totally dependent, they are not independent of the nodes on of the coordinates of node 1 and node 2. So, coordinates of node 2 entirely depend on coordinates of node 1 and node 2, which means if I put these 3 nodes in my A matrix will be singular, because this node is not independent of node 3 and node 2. If I have a situation like this, so this is node 1 and node 3. In this case, if I have a triangle, then the coordinate of each of the nodes is totally independent of other 2 nodes, but the same thing cannot be said when nodes lie on a straight line. So, physically A becomes singular when we have a straight line, when we have 3 nodes lying on a straight line. If there are 3 nodes which lie on a straight line, then we will have a matrix which will become singular, and when it becomes singular we cannot invert it, and if we cannot invert it we cannot express these C's in terms of U's. Okay. So, whenever a mesh is being generated, we have to make sure that the nodes never accidentally lie on a straight line. Now, in reality, what could also happen is I can have a triangle which looks like this 1, 2, 3. Okay. I could have a triangle which looks like this. Here, so it has 3 sides A, B and C. Here side C over A is extremely small compared to 1. In this case, the coordinates when C, in this case coordinate of node 3 and node 2 will be very close to each other, which means the A matrix mathematically it will not be singular because they do not lie on the straight line, but it will be almost singular. Essentially what that means is that the determinant will become an extremely small value, and when we are doing some computations we have round off errors and truncation errors, then even small changes in that small number in the determinant will cause large errors. So, what all this discussion tells us is that when we discretize a domain, we should not have elements with extreme aspect ratios. Okay. The same thing holds true for rectangular elements and so on and so forth. So, to avoid, I will call it almost singular A matrix, ensure that aspect ratio C by A is not very small, So, for a triangle you will have to calculate 3 aspect ratios, C by A, actually 2 aspect ratios, and B by A, and none of these ratios should be extremely small. In this case C by A is extremely small, in some triangles B by A could be very small. So, it should, so it's not very small, yeah, it should not be very small, that is when A is the longest side, because if you accidentally choose C as A and A as C, then it will be extremely large. So, a general rule could be that either it should not be extremely small or it should not be extremely large. If it is like 20,000, it is a bad element. If it is like 0.0001, this ratio, then again it is a bad element. It can create a lot of numerical problems in your solution. It may give you a solution, but those solutions may not be trustworthy. So, this is very important consideration. So, in general, narrow geometries for elements not good. Okay. Narrow geometries are not good. So, suppose you have an airfoil type of a structure and you want to analyze it. You can discretize it. This could be one element. In this case, C by A will be very small. Then how do you avoid this problem? You avoid this problem by making smaller elements, so that your A becomes small, then C by A is automatically starts becoming reasonable. So, this is important to understand, because sometimes you may have to take very narrow geometries, but when we are talking about narrow geometries, we are talking in context of this ratio. So, it is the ratio which is important. Okay. So, with that understanding, we now proceed, invert this matrix U is equal to A times C. So, the first thing we will do is we will develop an expression for A. So, A inverse equals 1 over 2 A E, and I will throw in some So, A inverse is the inverse of that A matrix, and it is equal to some 1 over 2 A E times this matrix, which is alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3. What are these alphas, betas? Alpha I equals xj yk minus xk yj. Beta I equals yj minus yk, and gamma I equals minus xj minus xk. Here I is not equal to j, is not equal to k, and I, j, k permute. What does that mean? Example, alpha 1, if I have to do alpha 1, if I have to calculate alpha 1, then I is equal to 1, j is equal to 2, and k is equal to 3. Okay. It is not a summation. Okay. So, then alpha 1 equals x 2 y 3 minus y x 3 y 2. Suppose I have to calculate beta 2, the beta 2 is equal to, so here I is equal to 3, no sorry 2, j is equal to 3, k is equal to 1, 2, 3, 1. So, beta 2 equals y 3 minus y 1. So, understood how we calculate? So, using this formula I can calculate alpha 1, alpha 2, alpha 3 and all other betas, and AE equals alpha 1 plus alpha 2 plus alpha 3 divided by 2. So, therefore, C1 equals 1 over 2 AE alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3. C2 equals 1 over 2 AE beta 1 U1 plus beta 2 U2 plus beta 3 U3, and C3 equals 1 over 2 AE gamma 1 U1 plus gamma 2 U2 plus gamma 3 U3. So, we understand how these relations came for C's. Basically, I have inverted A matrix and I have plugged that A mat inverse in this relation 3 or relation 4, 3 or 4. So, from that I can express C's in terms of U's. A is alpha 1 plus alpha 2 plus alpha 3 divided by 2. Okay. So, now we have accomplished our first goal, that is to express C's. What was our goal? We had to find C's in terms of U's, which we have done. Now, we have to find expressions for psi j's. So, now that is actually pretty straightforward. So, now we find psi j as a function of x and y. So, we know that u of e, which is a function of x y, is what? C1 plus C2 x plus C3 y. This equation is valid for which type of element? Only for a 3 noded triangle. If it is a rectangle, this expression will change. All this mathematics is going to change. If it was a rectangle, we will use the same approach, but this matrix, it will be 4 by 4. Okay. This matrix will be a 4 by 4 matrix. If it is a 6 noded triangle, which is a quadratic triangle, it will be a 6 by 6 matrix, and so on and so forth. So, the procedure is going to be the same, but all these details will change. So, u is equal to C1 plus C2x plus C3y, and we have already calculated the values of C's. So, this equals 1 over 2 AE, and what is C1? Alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3. So, this is alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3. So, that is my C1 plus C2x. So, that is beta 1 U1 plus beta 2 U2 plus beta 3 U3 times x plus gamma 1 U1 plus gamma 2 U2 plus gamma 3 U3 times y. Okay. Now, what we do is, so we have developed the expression for u. What we do is we collect terms involving u1, then we also collect terms involving u2, and then we collect terms involving u3. So, what we get is 1 over 2 AE u1 alpha 1 plus beta 1 x plus gamma 1 y plus u2 alpha 2 plus beta 2 x plus gamma 2 y plus u3 alpha 3 plus beta 3 x plus gamma 3 y. Agreed? This function I call it as psi 1 x y, because it depends on x and y only, and it is multiplied by no, it is, and of course, okay. So, actually I will, just to be consistent and accurate, I will divide this by 2AE, 2AE, 2AE. So, this function I call it psi 1 xy, this function I call it psi 2 xy, this function I call it psi 3 xy. So, we see that psi 1 is multiplied by u1, psi 2 is multiplied by u2, psi 3 is multiplied by u3. So, this can be expressed as j is equal to 1 to 3 uj psi j xy, where psi 1 xy equals alpha 1 plus beta 1 x plus gamma 1 y, psi 2 xy equals alpha 2 plus beta 2 x plus gamma 2 y. Yes. And psi 3 xy equals alpha 3 plus beta 3 x plus gamma 3 y times 1 by 2 AE. So, these are the three interpolation functions for 3-noded triangle. Three-noded triangle. Here what we see is that psi 1 depends on x and y, excuse me. So, all these functions, they are functions of x and y, and the values of alpha 1, beta 1 and gamma 1, they depend on the coordinates of these three nodes. If you see what are alphas, betas and gammas, these are nothing but they are functions of coordinates of nodes. So, alpha, beta and gammas, they are known constants. So, this is actually they are known constants, and these constants depend on the coordinates of the node. So, if I change from one element to other element, the coordinates of the node change, and because of that these psi functions also change. And while developing these psi functions, we have ensured that the value of these functions is same as Kronecker delta ij, because that condition was implemented where? When we were developing these first set of equations. So, here we had said that u of x and y is u1, right, which implied implicitly that psi 2 and psi 3 were 0, and so on and so forth. So, because of that reason, these psi's, they satisfy our requirements that they are 1 at their individual nodes, and at all other nodes they are 0, and their maximum value is only 1. So, this concludes the discussion for today and also for this week. What we will do in the next week is we will do a couple of examples for these linear interpolation functions, and then actually solve one or two problems for one 2-dimensional single variable problem. And also we will learn how to assemble these equations, because now we know how to develop these equations at element level, and then the next thing is we have to figure out how to assemble these equations at the assembly level and then impose boundary conditions. So, with that we conclude our discussion for today. Thank you and have a great day.